So we are now in part 9 of our discussions on instrumental methods of analysis. So for this portion of our lecture, we will be discussing the chromatographic methods, particularly gas chromatography and high-performance liquid chromatography. So first, let us discuss some of the theoretical aspects of chromatography. Alright, so first off, you have to remember that chromatography is actually a separation technique. Basically, in chromatography, what we want to do is to, when you have a mixture, you want to separate the components of this mixture. Okay, so for example, if you have here a mixture containing components A and B, alright, well, this is what you call column chromatography, no? So in chromatography, basically you have two phases. The solid, not always solid, but the one that is placed inside the column is what you refer to as the stationary phase. And then you have a free-flowing phase you call the mobile phase, no? As you know by now, the mobile phase can either be a liquid or a gas, no? Whereas for the stationary phase, it can be a solid, okay, or a liquid immobilized on a solid support matrix, okay. So what will happen is that the mobile phase, okay, so you place the mixture at the start of the column, then you pour in your mobile phase, okay. And we know that for column chromatography, the mobile phase will travel along the column via gravitational pull. Alright? Now, as the mobile phase travels through the stationary phase, okay, what will happen is that the sample will also travel along with this mobile phase. And this is the process which we call elution. Okay, and from experience, we know that in column chromatography, we can actually visualize, so usually if the components of the mixture are colored, we can actually visualize the separation of these components, okay, and we call this structures here as your bands, no, BANDS, no? So these are your bands, no? So parang rubber band, no? So yun yung na-imagine ng mga scientists, no, when they discovered this. Now in instrumental analysis, the only difference is that instead of using their eyes to see the progress of the elution process, we use a detector. Okay? So the detector detects the elution of the components, meaning to say the event, no, when they go out of the column, no, or the stationary phase. And since we are detecting the this elution process from the detector signal, okay, so normally we plot the detector signal versus the x-axis can be either the elution time or the elution volume, no? So yung well, if you did column chromatography in your thesis, normally what you record is the elution volume, okay? And this plot is what you refer to as the chromatogram. All right? Now, in the chromatogram, the bands, okay, are now appearing as peaks. Okay? So normally they appear as your Gaussian peaks. Okay? So this is now your chromatogram. Now, why do the components of the mixture separate, okay, as it travels along the stationary phase? Okay? So basically different solute, okay, or different components have relatively different degrees of attraction towards the stationary phase and the mobile phase. Alright, so they have different migration rates. Okay, so those components that are more retained or have slower migration rates are said to be more attracted to the stationary phase than the mobile phase. Vice versa, if you have a component that is less retained, meaning to say the migration rate is faster, no? The migration rate for this component is faster, then we say that this particular component is less attracted to stationary phase and, well, more attracted towards the mobile phase. So these differences in retention properties, or, well, you can look at it as migration rates, causes the separation of the individual components of a given mixture. Now, the goal of chromatography, of course, is the complete separation of components. Okay, and how do we improve separation? So this can be achieved by, number one, increase the rate of band separation. Or if you're looking at the chromatogram, you increase the rate of peak separation. So the more far away the two peaks are from each other, you say that the chromatographic process has higher resolution. No? So resolution in chromatography refers to the separation between these two peaks. And also, no, another important parameter that we look at chromatography is that we should decrease the rate of band spreading. Okay? So when you say band spreading in terms of this chromatogram, it refers to the peak width. Alright? Yung lapad ng peak. Alright? So when you say decrease rate of band spreading, it means to say that we want to have narrower peaks. Okay? So the narrower the peaks and the more far away the peaks corresponding to the components of the mixtures are from each other, then we have good chromatographic separation. Okay, so shown here are some of the general classifications of column chromatography. Okay, so when you say column chromatography, it refers to a type of chromatography where the stationary phase is placed on a column, a cylindrical column. Alright, now, well, from organic chemistry, you already know another type of chromatography, which you call your planar chromatography, wherein the stationary phase is in the form of a planar structure, such as that for TLC, thin layer chromatography, wherein the stationary phase is adsorbed, okay, on a usually that's a glass slide, or nowadays what you're using are aluminum material, no, aluminum sheets. Okay, or you have your paper chromatography, no, which is also a type of planar chromatography. Okay, so for paper chromatography, the stationary phase is actually the water molecules adsorbed on the paper. Alright, so that's paper chromatography. Now, for column chromatography, the general classifications are based on the mobile phase. Okay, so if you have a gaseous mobile phase, then you have gas chromatography. Alright, if you have a liquid, of course, no, liquid mobile phase, then you have liquid chromatography. Now, for instrumental methods, liquid chromatography is referred to as your HPLC, no, high performance liquid chromatography, wherein the mobile phase is pushed by high pressures, no, along a narrow column, no, which makes separation processes faster and in general more efficient, no, compared to your gravity liquid column chromatography. Alright, now a third type, okay, which we will not discuss in too much detail, is your supercritical fluid chromatography, wherein the mobile phase is what you refer to as a supercritical fluid. So from physical chemistry, I think you've heard this term, no? A supercritical fluid is neither a gas or a liquid, but a state, no, wherein this particular fluid has both properties of a liquid and a gas. Okay, commonly for SFC, what they use is supercritical carbon dioxide. Okay, and because of this unique property of supercritical carbon dioxide fluid, okay, separations are much better. All right, yung mga tawag dito, mga number of theoretical plates, mga column efficiencies, resolutions, are in general, no, equivalent to that of gas chromatography, even if you are processing samples that are for liquid chromatography. Okay, however, for in most laboratory settings, hindi pa ganoong kasikat si supercritical fluid chromatography. Although some manufacturers are trying to promote SFC, no? One advantage din kasi is that it has lower uh, chemical waste produced, no? Kasi sa liquid chromatography, one problem is that you produce a lot of wastes, no? Yung mga spent mobile phases, which are mostly organic solvents. Alright, so dagdag ano yun, no? Dagdag expenses yun sa laboratory, no, to dispose of those chemicals. Whereas for supercritical fluid chromatography, ang waste mo dyan is just carbon dioxide gas, no? So sa hangin lang lilipad. Alright, so specific methods under GC and HPLC. So for GC, you have your gas liquid and your gas solid chromatography. So yung kasunod, it refers to the phase of the stationary phase, no? So gas liquid refers to stationary phase that is liquid, that is usually bonded or attached on a solid support matrix, no? For gas solid, what you have there is a solid stationary phase. Now, important thing also to remember is the type of equilibrium or the type of interaction that you have in this particular chromatographic techniques, no? By the way, no, the manner by which your components elute along the stationary phase is via an equilibrium process wherein the analyte distributes itself between the stationary phase and the mobile phase repeatedly as it goes along the column. Okay? So to understand yung concept ng distribution equilibria, actually ito, no? So you can relate this to the topic discussed on distribution equilibria, no? Yun, di ba, yung if you have two immiscible solvents, okay, then you have your analyte dissolved in one of those solvents, which happens to also have some degree of solubility towards the other solvent. Then what will happen is that the analyte will distribute itself between those two immiscible phases or solvents. So, distribution equilibria. So, related yan dito sa chromatography. Okay, so nagdi-distribute din yung component analyte natin between the stationary phase and the mobile phase. Ang kaibahan nga lang dito, dumadaloy yung mobile phase, no? So, in essence, nagmamigrate yung ating solute components, okay, from the relative to the starting point. Alright? So, for gas liquid chromatography, partition is between gas and the liquid phases. Whereas for solid, this is basically an adsorption process, no? Kasi solid, no? Wala ka. Pag partitioning kasi, partitioning is related to solvent solubility. Alright? Solvent solubility. So, since liquid yung stationary phase mo, what you have there is partitioning. Okay? Kasi nagdi-dissolve, quote-unquote, yung analyte mo into the liquid phase. Next, you have your liquid chromatography. Okay, so one advantage of liquid chromatography is you have this diversity of methods based on the equal diversity of equilibrium. Okay, or equilibria that can be played around, no, in liquid chromatography. So first, you have your liquid chromatography, wherein you have a liquid stationary phase. So basically, this is partitioning, no? So again, very much related to your distribution equilibria for solvent-solvent extraction, yung concept. Next, you have your liquid-solid, or also called, of course, your adsorption chromatography. So again, the process is adsorption. Now, another is your ion exchange, all right? And the stationary phase is a unique material. You refer to this as your ion exchange resin, no? So as the name implies, This type of chromatography is very useful for the separation of ions, no, in a mixture. All right. So the principle here is ion exchange equilibria. All right, which we will also discuss on the latter part. Okay. Next, you have your size exclusion chromatography. All right. Basically, these are you have a polymeric solid. All right, and the stationary phase are the liquid in the interstices of a polymeric solid. Okay. So basically, what you have here is sieving, partitioning or sieving. As the name implies, size exclusion separates your solute components in terms of their relative sizes, okay, or relative molecular weights, okay, instead of their relative affinities, no, towards the stationary phase. So I think kaibahan sa size exclusion chromatography. Then lastly, you have your affinity chromatography, wherein you have a special group-specific liquid bonded to a solid surface, okay? And then, partitioning din naman nangyayari dito. Now, when you say affinity chromatography, you need to have a very, you need to utilize a very special type of interaction. So, one example of affinity chromatography would that of using the antigen-antibody interaction, for example. Okay, so what you can do is you can attach specific antibodies, all right, onto a solid support matrix, so that when you elute a sample containing a particular mixture of antigens that have specific interaction or binding specificity towards the antibody used as your stationary phase will be retained longer compared to those that do not interact with this uh, particular antibody. Or another example of affinity chromatography would be your chiral chromatography, wherein you use specific um, stereoisomers, all right, or specific enantiomers as your stationary phase, so that if you have a mixture of enantiomers, okay, and you want to separate these enantiomers, those that fit to the stereo structure of your stationary phase will be retained longer than the other components, no? Um, yeah. So in liquid chromatography, actually, if you have, for example, a racemic mixture, and you're just using, say, liquid-liquid or liquid-solid chromatography, you won't be able to separate a racemic mixture, no? Because as we all know, the enantiomers, okay, no, enantiomeric pairs have the same physical properties. Okay, yung partitioning, ano yan eh. Basically, physical process yan eh. Alright? So, if you want to separate a racemic mixture of an enantiomeric pair, then the only choice that you have is to use chiral chromatography, which is basically a type of affinity chromatography. Okay, so next we have the some terminologies, no, regarding your chromatogram. All right. So for instrumental liquid chromatography, HPLC, normally the chromatogram is represented with the x-axis referring to the retention time. Okay. So the retention time, so that is T sub R, is the time, okay, starting from the moment of injection of the sample into the chromatograph until the appearance of the peak corresponding to the elution of your component, okay, of one of the components of your mixture. So the time that elapsed is referred to as your retention time. Okay. Now T sub M is referred to as your dead time, or also called your void time. Alright? So this peak, okay, represents those components of your mixture that you injected that were completely unretained in the stationary phase. Meaning to say, wala siyang, ito yung mga components na walang interaction, no, with the stationary phase. No? So, sumabay lang siya mismo sa anode ng mobile phase. Alright? So, the void time or dead time actually represents to you the flow rate or the average flow velocity or linear velocity of your uh, mobile phase, no, as it passes through the stationary phase column. All right. Now T sub S, this is just the difference between the retention time and your dead time. In some books, this is represented as T prime R. So T prime R or T sub S is referred to as your corrected retention time for this particular solute. No? So for the corrected retention time, it just shows you the actual time, alright, that this solute spent inside your stationary phase. Okay? Now, ideally, your peak should be Gaussian in appearance or normally distributed. So when you say Gaussian, symmetric. Okay? No? Equal yung distribution dun sa left at right side, no, from the center of the peak. Then of course, the narrower the peak, the better, no, kasi ito yung sasabi nating lower yung spread of the band. Okay? Now, the void time, no, or yung dead time na peak, in real life situations, it does not appear always, no, when you run your chromatogram. Alright? So, for theoretical discussions, we normally show a dead time peak. Okay, as you will see later, no, yung mga computations, no, yung like yung mga selectivity factor, retention factor, no. Minsan may mga equations do na kailangan alam mo yung dead time. Okay? Pero yun nga, sa practice ng chromatography, hindi lagi ito nakikita, no? Kasi minsan yung mga unretained species maaaring invisible doon sa detector na ginagamit. Okay? Now, shown below are some of the tawag dyan, yung mga distortions, no, doon sa iyong chromatographic peaks. Okay? So here, you have yung fronting and your tailing. So sa fronting, ano nangyayari sa fronting, no? So asymmetric siya, no? Mas broader yung sa left side. So this means that some of the components, no, being eluted, no, represented by this peak, are eluted faster than the bulk of the component. Okay? So normally fronting occurs when you overload the sample injected into the chromatograph. Ibig sabihin, masyadong concentrated yung ating analyte, no, doon sa sample. So to reduce fronting, you need to dilute your sample. Okay? Now, another is your tailing. So sa tailing naman, merong mga nahuhuli na solute molecules. Alright? Compared doon sa bulk nung nag-elute na nung component na yun, no? Okay? So, tailing, maraming reasons for tailing, no? One reason could be that hindi optimized, no? So, the parameters, the chromatographic parameters are not optimized. So, maybe you need to modify the mobile phase, or maybe you need to change the stationary phase, no, nung chromatograph. Another reason, no, if you're doing GC, this is an indication na there is some deterioration in the stationary phase, no, in the column, no, and even in liquid chromatography, no, when you see tailing, this can be indicative of column deterioration. All right, yan. So again, ideally you want to have a symmetric peak. no, in the industry, no, if you work in say pharmaceutical companies, no, yung mga tinatawag na tailing factor, pwede mo i-compute yon using the system, and there is only a maximum level of tailing that is allowed, all right, by this regulatory uh, offices or regulatory bodies. Okay, so you need to be conscious, no, about these asymmetric or deformities, no, in your chromatographic peaks. Okay, so here are some of the pertinent equations used to describe a certain um, chromatographic parameters, no, or even the conditions, no, of a given chromatogram or chromatographic process. So first you have your partition coefficient, no? So the partition coefficient is, well, an equilibrium constant actually, no? So remember that your analyte actually partitions itself, okay, between the stationary phase and the mobile phase. Okay, so the equilibrium constant for that partitioning process is referred to as your partition coefficient. Alright, so the concentration of the analyte solute in the stationary phase over the analyte concentration in the mobile phase. No? So as the equation implies, the higher your partition coefficient, it means to say that your solute is more attracted towards your stationary phase. Hence, you have higher retention time. And vice versa, the lower your partition coefficient is, it means to say that the analyte is less retained by the stationary phase. And then you have shorter retention time. Alright? Okay. So next, you have your capacity factor, or in more modern text, you call this your retention factor. Alright, so represented by small k prime. So this is simply the corrected retention time divided by the dead time. Alright, so the capacity factor just represents to you yung relative migration rate of that particular solute. No? So the lower your retention factor, okay, it means to say that your analyte is less retained. And the higher your retention factor, there is greater retention of the analyte in the stationary phase. Next, you have your selectivity factor, okay, given by alpha. So this simply relates the relative retentions of two adjacent solute peaks. Okay? So you have here the equation, no? So yung corrected retention time for solute B over the corrected retention time for solute A, where B is the more retained species, no? So you may higher retention time. All right? Because alpha has a value of 1 or greater than 1. So when your alpha is equal to 1, it means to say that there is no separation between the two solute peaks. Okay, so the greater the alpha, the greater the separation, no, between these two adjacent peaks, which is better. All right. Next, you have your number of theoretical plates. This particular parameter is an indicator of column efficiency. So, how well can your column parameter, no? Pag sabing column parameter, ito na yung combination ng mobile phase composition, stationary phase composition, flow rate, no? So, all of those things, no? Column temperature, alright? So, all of those things, no? So, number of theoretical plates, this is an imaginary number, actually. So, this is computed using this equation. So, you have the column length, usually in centimeters, divided by the height equivalent to theoretical plate, or HETP. Okay? or you can also call this your theoretical plate height. In some books, it's just being referred to as your H. Alright? So the unit for length and theoretical plate height is usually expressed in centimeters. Alright? Where H is centimeters per plate, no, actually. No? So yung final unit mo is plates. Alright? So here, the higher the number of theoretical plates, the more efficient your column is in terms of separating the components of a mixture. Alright, now the number of theoretical plates, no, although theoretical, is usually computed based on your chromatogram. Alright, so by if you have a single peak, for example, alright, so this is the equation, no? So you get the retention time for that single peak, then you square that value, then multiply that by 16. Then divide it by the square of the peak width. So the peak width is measured from the base of the chromatographic peak. No? So you just measure the length, no, of the base of your peak. Now, since measuring peak widths is quite arbitrary, no? Kasi hindi mo alam kung saan nag-uumpisa, saan nagtatapos, no, yung chromatographic peak. Another better way is by using the W1 half. This is the peak width at half height maximum. Okay? So maybe we can draw that, no? So kunwari ito yung iyong peak, all right? So by measuring this length, no? Ito yung peak width. But if you want to measure the peak width at half height maximum, so you get the height, all right, of the peak, no? So the baseline can be easily established, no? So you get yung half nan, and then measure the width dito, no? So ito yung iyong half height max, peak width at half height maximum. All right, so this is more convenient, no, to measure. So just take note of this equation. Okay. Well, before we move to resolution, so things that you have to remember here, no. So at constant column length, all right, to improve the number of theoretical plates, you have to have a lower value of H. Okay, so the lower H value or HETP value, the more efficient your column becomes. Okay, so you have to remember that particular relationship, because later, no, when we discuss Van Dimter equation, okay, it's normally represented in terms of your theoretical plate height. Okay. Next, you have your resolution. So resolution refers to the degree by which two adjacent peaks are separated from each other. No? So ito yung computation. No? So you have the difference between the retention times of peak B and peak A, where peak B has the higher retention time, times 2, yung difference, then divided by the summation of their respective peak widths. Okay? So the minimum value for resolution should be 1.5 for you to say that there is complete separation between two adjacent peaks. If it's less than that value, then you have significant overlap, no? So hindi ka pwedeng mag quantify or whatever, no? Invalid yung lalabas sa chromatogram, no? So you need to modify some of the chromatographic parameters. Okay, so at least 1.5 or greater. All right, so that will give you a good resolution. Okay. Sorry, I forgot one thing. No, for the number of theoretical plates, if you have more than one peak, and you want to compute for the number of theoretical plates, all you have to do is to compute for the n value corresponding to all of the peaks that is shown in your chromatogram. Then you get the average. Alright, so that you can obtain the average theoretical plates, no, number of theoretical plates for a given chromatographic parameter. Okay, so some other pertinent equations. Okay, so you have here a relationship of resolution with theoretical plate height. Okay, this is another way of writing this equation. And this one shows you the relationship between retention time and resolution. So what can we observe here, no? So here, the higher the resolution, the higher the number of theoretical plates. Okay, so another way of saying that is that the greater yung theoretical plates mo, the higher the resolution, no? And this shows us yung sasabi nating column efficiency. An efficient column will give you greater separation, hence greater resolution. Alright? Here shows you yung retention time. So ano masasabi natin dito, no? So the lower your theoretical plate height, the lower the retention time becomes, no? And in chemical analysis, better yun, no? It's better to have shorter retention times because it will lead to shorter run times, no? And shorter run times will give you more time, no? To analyze more samples, no? Because you only need shorter time to produce the required chromatogram. Alright? So you just need to remember these relationships. So shown here are the different kinetic variables that affects your band broadening. So nasabi natin kanina sa umpisa that band broadening should be reduced. Okay? In theory, if you have, for example, you have two components in a mixture, no? Let's call them A and B. If we are saying that the reason for separation for these two components ay based sa relative migration rates or their corresponding affinities, alright, towards the stationary and mobile phase, in theory, all of the solute molecules, that is component A, should be eluting at the same time. Alright, so instead of seeing peaks, you should be seeing vertical lines. Kasi sabay-sabay silang lumalabas eh. When you have a peak, it means to say that some of the solute molecules of component A elutes a little bit faster, okay, than the rest of the molecules, and some are even retained more than the rest of the solute molecules, no? And since ideally you have that Gaussian distribution, it tells us that the occurrence of some solute molecules eluting faster and those that are eluting a little bit later have equal probabilities. Alright? So, yun yung ibig sabihin ng iyong symmetrical peak. Alright? So, ideally, you want to have narrow peaks because that will entail na kakaunti inauuna at kakaunti rin yung mga medyo nahuhuling solute molecules, no? So, bakit hindi sila sabay-sabay lumalabas, no? As a single line. Bakit kailangan maging peak? So, this is discussed here. So, one of the variables, no, is this one. This is referred to as your variable A. And this is called your eddy diffusion term or the multiple path diffusion term. Okay, so let's use the pen. So, this is your term A. Okay? So, ano sasabi ni term A? Sasabi ni term A, if you are using solid, okay, stationary phases, normally in terms of particles yan, no? Or even liquid bonded on solid particles, alright? So, basically, what you have there is you have a densely packed column. Okay? Now, the mobile phase, along with the solute, will actually travel along these interstices. Alright? Along the interstices or the gaps between these particles. Now, because of the random manner by which these particles are compressed or packed together, it creates random pathways, no? Some pathways are longer than the other pathways. And because of these differences or multiplicity in the pathways, you have differing rates, no, by which your solute can travel across the column. No? And one reason kung bakit may ibang nauuna at may ibang nahuhuli. Okay? Now, in relation to your column efficiency, so here we are going to use your theoretical plate height. Okay? So, in relation to your theoretical plate height, no? Ito yung relationship, no? So, term A is equal to H. Meaning to say that the column efficiency attributed to your multiple path term, alright, no? So, the term A directly contributes to the theoretical plate height. So, here, the lower, alright, the lower your term A, the lower would be your theoretical plate height, which is good. Okay, so again, this is related to the packing density of your stationary phase, no? So, lagyan na nga natin yan. No? So, yung packing density, sorry, I'm using my mouse for writing right now. Alright, so you have the packing density, also the particle size. Okay. So, the particle size will contribute, no, to your multiple pathways. Okay. So, ideally, the smaller the particle size, the more evenly distributed your gaps or interstices between the particles. No? So, it will lead to lower theoretical plate height, no, in terms of your term A. Next, you have your term B. So, the term B is referred to as your longitudinal diffusion term. So, ano ibig sabihin nun? So, if you're going to look at the elution of a particular solute inside a column in slow motion, you have to remember this, no? Kung ito yung original band, alright, this particular region is a region where you have high solute concentration, no? So, you have high solute concentration. Now, as this band travels along this column, what happens, no? Or what would happen? Remember that the regions on either side of the band are regions wherein you don't have solute, no? Or you don't have that particular solute. So, as no, from Gen Chem, no, what will happen? This band will actually diffuse or spread along its side. Alright? So, that's what you refer to as longitudinal diffusion. And that's one of the reason why your peak spreads, no? Or yung band mo, nagkakaroon ka ng band spreading. Alright? Now, in relation to your theoretical plate height, this is the equation. Okay, so you have the B turn over mu, no? Where mu is your average linear velocity, which is related to the flow rate. Alright? Ang flow rate is actually in terms of milliliters of the mobile phase per minute, no? So, ito yung rate by which your mobile phase travels, no, across the column, no? But in the equation is actually the average linear velocity lang ng mobile phase. But what does this tell us, no? As sasabi lang natin dito ay the lower, no, if you decrease the flow rate, what will happen, no? If you decrease the flow rate, your H value will increase, no? And why is this? No, because you're giving the band more chances to spread out or to diffuse longitudinally. Okay? But if you increase the flow rate, so the higher the flow rate, ano mangyayari? Bababa yung theoretical plate height, no? Because you are preventing your band to diffuse, no? Or you're not giving your band enough time to diffuse. Okay? So this is the relationship of diffusion term with theoretical plate height. Then lastly, you have the so-called C term or the finite mass transfer term. Alright? So, sasabi ng finite mass transfer term. So, remember that your analyte, okay, your analyte actually distributes itself or partitions itself repeatedly between the stationary phase and the mobile phase. So, palipat-lipat siya dyan. Okay? Now, if the flow rate is low, no, or mabagal, no, mabagal, slow rather, no. So mabagal yung flow rate mo, so if slow flow rate, you are allowing your analyte from the stationary phase to diffuse back to the mobile phase, no. So you're giving it enough time to go back and forth. But if you increase the flow rate, what will happen is that the solute that is in the stationary phase will not have enough time to equilibrate back to your mobile phase. And because of this, you have here a band spreading phenomenon. Alright? Kasi masyado mabilis yung flow rate, hindi agad nakakalipat, no? Yung solute from the stationary phase going back to the mobile phase. And also, equally the same, those solute molecules in the mobile phase will not have enough time to go towards the stationary phase. So again, in relation to your theoretical plate height, this is the relationship. So H is equal to C times mu. So here, you have a direct relationship between the mobile phase flow rate and your theoretical plate height. So dito, sinasabi, the lower your flow rate, the lower your theoretical plate height. Okay? Because you are giving your solute molecule enough time to equilibrate between the two phases. But if you speed up, okay, the flow rate, you will get higher theoretical plate height, no? Because you are not giving your molecules enough time to undergo equilibration. So as you can see, term C and term B are two conflicting variables, no, in terms of flow rate. So the question here is, what is the optimum flow rate wherein you can get the maximum column efficiency in terms of the lowest theoretical plate height? So the answer to that is you need to really optimize your flow rate, no? It's something that you cannot determine from calculations, no? You have to determine this empirically or experimentally. Okay, so the combination of these three kinetic variables is given by your van Dimter equation, no? So ito yung kilala niyo equation sa chromatography. So the van Dimter equation simply relates the flow rate and the corresponding kinetic variables, all right, with your theoretical plate height. And again, the optimum flow rate is found to be the one that corresponds to the lowest H value. So in summary, what are the things that we can do to decrease band broadening and improve the overall column efficiency, no, or the efficiency of the chromatographic parameters? So first, as we mentioned earlier, you use smaller packing diameter, no? Kasi the smaller yung packing diameter, you have smaller void volumes, no, between the gaps, no, in the particles, so thereby reducing yung multiple path term. All right. In liquid chromatography, the problem with using smaller packing diameters is that we usually experience higher back pressure, no? So mas mataas yung pressure ang required to push the mobile phase into the column, no, if you're using finer particles. So that is the development that is being utilized now with what you call your UPLC, no? Yung tinatawag na ultra high performance liquid chromatography. So this is a type of HPLC system that has a more powerful pump, no? So since you have a more powerful pump, no, it can actually withstand higher back pressures, no? So here you can use columns with finer stationary phase particles. So ang magiging advantage ito is that you can afford to use higher flow rates, no? Higher flow rates would mean lower retention times, no? So hence you have lower run times, no? So yung mga dating nirarun sa conventional HPLC that will take say 10 minutes, no, per sample. Sa UPLC it will only take around 2 to 3 minutes, no? So you have a reduction by a factor of 5 halos, no, dun sa iyong total runtime, and that will actually improve, no, yung number of you will have greater number of samples, no, that you can run, no, in your system. Okay, next you can use smaller column diameters, no? So with smaller column diameters, this would improve again your term A, no, lower term A kasi mas konti yung pathways na ma-generate, and also in effect, no, this will also decrease your term B, no, yung effect ng term B, yung longitudinal diffusion, no, because you have smaller radius, no, wherein pwede diffuse yung iyong analyte molecule. Alright, if you're doing GC, lower temperature, better, okay, because diffusion is temperature dependent then, no? The higher the temperature, the more the greater the kinetic energy na meron yung solute molecule, so mas faster yung diffusion process niya. So if you have lower temperature, then you have lower kinetic energy for the solutes. Okay, if you're using open tubular columns, no, or capillary columns in gas chromatography, then the thinner yung layer of stationary phase, the better, okay? Because again, here you are lowering yung term C naman, yung finite mass transfer term, no? Because you have fewer amount of stationary phase wherein your analyte can diffuse into. Okay? Ayan. Interesting, no? Fact about your capillary columns is that wala itong term A sa Van Demeter equation. Walang multiple pathway term, no? Simply because you don't have any particles, no? Packed particles. Okay? So ito yung isang exemption, no? Ito yung Van Demeter equation for capillary columns is just represented by the longitudinal diffusion term and the finite mass transfer term. Alright? Then of course, no, as we shown earlier, you need to optimize the flow rate, okay, for the for your chromatographic process. Alright, so this is it for module 9-1. So again, the self-assessment test will be posted in your FB group page.